Hi. Now that we have already covered a large range of fundamental topics in astronomy, in this two-part series, we'll move a step forward and discuss about the interior of stars in a little more depth. So join us as we figure out the physical processes happening in the interior of stars. Let's begin. To dive into the interior of stars, we will have to understand the journey of a photon as it is created in the innermost core at the center of the star via nuclear fusion and makes its way out to the surface from where it may be observed by us. In case of the Sun, for instance, we know that it takes light 8 minutes 20 seconds to reach Earth from the surface of the Sun. But did you know that it actually takes 100,000 to a million years for a photon to reach the surface of the Sun from its core? This difference in time scale is primarily because a photon never travels in a straight line. It can be scattered, absorbed, and then re-emitted hundreds and thousands of times before it reaches the surface of the Sun. Think of its journey like a drunk man's walk. It goes 3 steps forward and 2 steps backwards. As a consequence, it reaches the surface thousands of years after it is produced in the core of the star. Now we know that dust is an important part of the interstellar medium. As we have discussed in our earlier videos, dust absorbs the short wavelength photons but allows the long wavelength light to pass through. Let's try to quantify this idea. In order to understand the interaction of radiation with matter, we consider atoms as spheres of radius r. So a beam of photons sees an atom as a circle of area pi r square, and if the beam is in this area, it will get absorbed. This area is actually known as the cross-section, represented by sigma. This cross-section is the probability of the photon to get absorbed in a material. So now if we consider a cylinder with these atoms in it, we would like to know how much radiation which is incident on the face with area A gets absorbed in the material. The volume of this cylinder is given by the area of the face multiplied by the length of the cylinder L. If the cylinder has small n number of atoms per unit volume, then the total number of atoms in the cylinder, given as capital N, will be equal to NaL, and as a result, the total cross-section or the total probability of an incoming photon to be absorbed is given by the quantity small NaL into sigma. This assumes that the incoming beam sees all the atoms, which means that no atom shadows the other. This condition will be met only if the spheres occupy a very small fraction of the area of the end surface, which means sigma total is much smaller than the area of the face capital A. So the fraction of the radiation which is absorbed will be equal to the area covered by the face. In other words, this ratio of sigma divided by A is given as the quantity NL sigma or tau. The letter tau here is called the optical depth. And so the condition that sigma total is much smaller than the area of the face of the cylinder capital A translates to tau much smaller than 1. For example, if tau is equal to 0.01, it means that 1% of the incoming radiation is absorbed. In general, the cross-section area sigma or tau, the optical depth, are a function of lambda, and as a result, in many of the text you will find that these two quantities are represented with a subscript lambda. These are a function of wavelength because if a photon of a particular wavelength is closer to the wavelength of a spectral line, the cross-section for that particular photon will be very high. But if the photon's energy or wavelength is not close to a spectral line, its cross-section will be much lower. The quantity NL, that is the number density times the length, is measured in units of number per unit area. That is the number of atoms in the full length of the cylinder per unit surface area. So, if you consider the cylinder to have a face surface area as 1 meter squared, that is A is equal to 1 meter squared, then NL is the number of atoms in a cylinder of length L. This quantity is called the column density. So, optical depth depends upon the properties of the material, that is the cross section, the density of particles, and the total size of the absorbing region. The dependency on these quantities can be separated taking into account the absorption coefficient represented by the Greek letter kappa. It is also often represented with the subscript lambda to stress the fact that just like the optical depth, the absorption coefficient is also a function of wavelength. Absorption coefficient is defined as the optical depth per unit length through the material, or in other words, the number of absorptions per unit length. It is given by n sigma by rho. Inverse of this quantity is called the mean free path, which is the length that a photon can travel without getting absorbed, assuming that the optical depth is much smaller than unity. But what if that is not the case? Well, then we consider the material divided into very thin layers, each with optical depth d tau much smaller than 1, so that the fraction of radiation absorbed in the first layer is given as I naught d tau, and passing through to the next layer, it is given as I naught into 1 minus d tau. So the change in intensity due to absorption in the first layer is actually minus I naught d tau. So the cumulative effect of the radiation getting absorbed at each stage can be computed using the integration and leads to the fact that the final intensity is I naught times exponent of minus tau, where I naught is the intensity of the incident radiation and tau is the optical depth of the material. Of course, as we have discussed, in the optically thin limit, that is when tau is much smaller than 1, we get I is equal to I naught into 1 minus tau. Now, as shown in this figure here, since e to the power minus tau decays very quickly with increasing tau, in order to escape from the surface of the sun, the radiation must be coming approximately from within one optical depth of the surface. This explains why we only see the outer layers when we are seeing the sun or any other stars. Since kappa is a function of wavelength, at different wavelengths we will see different depths. At larger kappa, we do not see very far into the material or the star and vice versa. Astronomers take advantage of this fact to study the conditions at different depths below the surface. So far, we have only looked at absorption, but remember that radiation can also be emitted at each layer. So taking into account all such effects require complicated radiative transfer models to be calculated, requiring powerful computers. If light of wavelength lambda and intensity I in enters a cloud made up of particles with cross-section sigma, and this light has some intensity I out when it leaves the cloud, the ratio of these intensities is given as e to the power minus tau. Tau, as we have already discussed, is the optical depth of the cloud. So practically, the change in magnitude of the light caused due to the presence of interstellar extinction can therefore be given as this expression, implying that the extinction is 1.086 times the optical depth. We used subscript lambda for tau to emphasize that extinction is indeed a function of lambda. Therefore, whenever the magnitude of an object is measured, it should be corrected for interstellar extinction, that is A. The impact of extinction diminishes with the wavelength of light, which means that the shorter wavelength light is affected much more than the light at longer wavelength. It is due to the optical depth that the edges of the sun look darker relative to the center. This phenomena, also seen among other stars, is called limb darkening. Basically, this is a consequence of the fact that the intensity coming from near the edge of the sun is lower and the line of sight passes farther from the center of the sun, that is, at a larger optical depth. This causes the path length through the sun to decrease and pass through less dense regions, making the solar disk appear darker towards the limb, that is, the outer edge. The amount of limb darkening allows astronomers to determine the temperature distribution in the sun. It could also tell us a lot about the properties of the stellar atmosphere if we could see it, for example, during a solar eclipse. This brings us to the key point that when we measure the color of an object, say B minus V, it must be corrected for interstellar extinction. This change in color of an object due to the intervening dust is known as interstellar reddening. More is the extinction, higher will be the reddening. The term reddening itself implies that the blue or short wavelength light is shifted to redder or longer wavelengths. Now, if we take the ratio of extinction at any wavelength lambda relative to extinction in some reference band, say V band, and plot it as a function of the inverse of lambda, we get a curve of this form known as the extinction curve. You can learn more about this in our earlier video on the interstellar medium, a link to which is provided in the description below. We know that stars come in different sizes. It is fascinating to note that the laws of physics which explain processes around us are also active in different regions of stars. Stars of different masses show regions with convective and radiative transport dominance in different parts of the stars. What is convective and radiative transport, you ask? Well, the energy transport in a star can happen in three ways. In radiation, photons carry the energy, while in convection, energy transfer by mass motion of a fluid takes place. I'm sure you have seen the tea leaves or grains of rice going up and down in water when it's boiled. As the water is heated from below, in a pan, the rice or tea leaves gain energy and come to the surface, transfer that energy and go back down. It looks like they are going in a circular motion vertically in the pan. This is what happens in convection. In conduction, two surfaces which are in direct contact with each other experience transfer of heat from the hotter to the colder surface. So in the next video of the series, we will discuss the 4 different equations that determine the mode of transport of energy in stars of different sizes. I really hope you learned something new today. Please do like and subscribe to our channel and share our content with other astronomy enthusiasts. I'll see you next week. Until then, take care.